Have you ever wondered why humans don't just randomly guess the meaning of sentences? Like, why does the cat sat on the mat feel so different from Matt the on-sat cat, even though they have the same words? It turns out our brains use smart, structured strategies to parse language, something that's not so obvious when you're just looking at the words themselves. This study dives into a big question. Why don't humans use random strategies to understand language? To explore this, researchers built a kind of language lab using AI models. They wanted to see if random guessing, like flipping a coin to decide how words connect, could work as well as our human-like structured approach. Spoiler, it doesn't always. Let's break it down. The team tested two main ideas. First, they used more complex meaning spaces than previous studies. Instead of simple lists of attributes like color, red, shape, round, they used a language with nested structures. Think of it like parentheses in math. A plus BC versus a plus BC. These structures are harder to parse randomly because the order matters a lot. Second, they added something called surprisal, a measure of how unexpected a word or phrase is in a sentence. For example, the cow flew a plane is more surprising than the plane flew a cow. By including surprisal in their AI models, they mimicked how humans naturally process language, where unexpected words grab more attention. What did they find? When the meaning space was simple, random parsing worked pretty well. But when the structure got complex, like those nested parentheses, random strategies fell apart. The AI models struggled to keep up, leading to confusing or incorrect interpretations. Plus, when surprisal was factored in, the random models had to work much harder, like trying to solve a puzzle with missing pieces. So why does this matter? Well, it suggests that human language isn't just about memorizing words. It's about understanding structure and context. Our brains use built-in rules to make sense of sentences, which makes communication efficient and reliable. For AI, this means building models that mimic these human-like strategies could lead to smarter, more intuitive language systems. Next time you're reading a sentence, think about the hidden structure behind it. Our brains are doing way more than just matching words. They're decoding a complex hierarchical puzzle. And that's why random guessing. It just doesn't cut it. Thanks for watching. If you found this intriguing, hit subscribe for more deep dives into AI, language, and the science behind it all. What do you think? Do you think hierarchy is key to human-like communication? Let me know in the comments. Ever wondered how AI learns to communicate? Or why some language models struggle with complex structures while others thrive? Today, we're diving into a fascinating study that reveals how the structure of communication matters, especially when it comes to hierarchies. Let's start with a simple analogy. Think of parentheses in math. When you see a plus BC, you need to track not just how many open brackets there are, but also their order. This is what researchers call a Dyck task, a test of hierarchical understanding. For k equals one single type parentheses like just and, it's manageable. But when you add multiple types like and for k1, it gets way trickier. Here's the twist. Some AI models called random branching models are great at simple tasks but crash when hierarchy gets complex. Why? They can't keep track of the order in which different brackets were opened. It's like trying to follow a recipe by only counting how many steps you've done, not remembering which ingredients went in first. The study tested this by comparing models. One used a hierarchical semantic space, think of it as a structured map of meaning, while others relied on simpler, flat representations. The results? When tasks got complex, K1, the hierarchical models outperformed the random ones. Their ComAcc scores, a measure of communication accuracy, stayed steady, while the random models overfit, meaning they worked well on training data but failed on new, unseen examples. But there's more. The researchers also added a surprisal factor, which measures how unexpected a message is. Here's what they found. Random branching models struggled with unfamiliar meanings, interpreting messages as overly surprising. This high cognitive load isn't efficient, like trying to read a book in a language you only half understand. So what does this mean? It suggests that for AI to communicate like humans, it needs structured, hierarchical thinking. Flat, random approaches might work for simple tasks, but when complexity rises, the system breaks down. This isn't just about code. It's about how we design AI to understand and generate language in a way that mirrors our own cognitive processes. Next time you see an AI model struggling with a complex sentence, remember, it might not be smart enough to handle the hierarchy. And that's where the real challenge lies. So how did the researchers test these ideas? Let's walk through their experiments step by step. First, they set up a model with 3 key operations, pop, push, and read, and limited their strength to a maximum of 2. Think of these as the model's tools for handling nested structures, like parentheses in math. To fine-tune the model, they used a special math tool called Atom, which adjusts the model's settings during training. They kept the learning rate super tiny, 0.0001, and added some rules to prevent the model from getting too confident in its guesses, like a teacher reminding a student to stay open-minded. The data was split into 90% for training and 10% for testing, like a practice set and a final exam. Each training round used 8,192 examples at once, a huge batch size. And they ran this process 15,000 times, giving the model plenty of chances to improve. Then in a second experiment, they tweaked a parameter called beta, which controls how much the model forgets past knowledge, to 0.001 and trained it for 10,000 rounds. But the real twist came in a preliminary test where they tried different, meaning space, configurations, like varying how the model represents abstract ideas. They tested setups like 2 attributes with 64 values, 3 with 16, and so on. What did they find? As shown in their results, the model performed best under random branching conditions, where decisions weren't strictly scripted. This boosted a metric called ComAcc, communication accuracy, suggesting that introducing randomness helps machines learn more effectively. Importantly, this wasn't just a fluke. It matched earlier studies, proving that randomness itself is a powerful tool for improving AI performance. So even though the math sounds complex, the takeaway is simple. Sometimes, letting things get a little unpredictable can lead to smarter machines. Stay tuned as we dive deeper into what this means for the future of AI.